I want to say thank you here to the organizers and to my co-authors for helping give a brief glimpse into advances that we've made since 2009 when the term blue carbon was first coined. There's a lot of action going on at the coast, as you know. And within the coast zone, there are these distinct coastal vegetated ecosystems that maintain some of the highest rates of carbon sequestration and soil storage of all global ecosystems. So we mostly think of mangroves, salt and fresh marshes, tidal freshwater marshes, and seagrass meadows, but other systems like kelp burial may be becoming important. While they're just a small fraction of the global land, their soil formation is continuous with sea level rise, and storage can be for millennia. So 2 to 25 petagrams are currently estimated as stored in the land-ocean fringe, and they're predominantly in soils at potential annual rates of about 1 petagram per year with active soil accretion. Those numbers are, of course, difficult to extrapolate and model due to all the interfaces going on in this zone in terms of time, space, management. The land-ocean boundary is highly complex and variable. It's where more than 70% of the world population lives. Land management can be even more important in altering the direction of carbon flows in the physical location. So the Department of Energy in particular is one that's pushing forward on improving modeling of these coastal terrestrial aquatic interfaces. And so tune in for the DOE town hall for more on that. So despite uncertainty, we've generated some constraints in understanding soil carbon and its vulnerability. One is that soil carbon densities, they cluster around 30 milligrams per cubic centimeter, even down core, due to differences in weights and in packing densities of mineral and organic soils. Two is that increasing accommodation space as per sea level rise leads to accretion of both mineral and organic sediments until rates are too high to overcome and then the marsh drowns. This is probably the most important modeling need to understand the potential for blue carbon in specific sites and globally. Ecogeomorphic responses are clearly important. The rates of increasing accommodation space through sea level rise and tectonics have been shown globally as the best predictor of soil carbon preservation. For mangroves in particular, down core carbon storage is clearly variable with clastic sort of deltaic sediments and carbonate sediments. And if you can map those geomorphic settings, you can upscale soil carbon stocks globally, again, with a clustering of about 30 milligrams of carbon per cubic centimeter. Beyond geomorphology, salinity is a key geochemical driver. So for example, gross primary productivity, as seen in eddy covariance data and in remote sensing products from satellites like MODIS, are showing salinity playing a key role in productivity. Methane, salinity is the key predictor. In the current data sets we have available, saline wetlands just do not emit very much methane at all. They have a cutoff at about half strength salinity, about 18 parts per thousand. But as we get more and more eddy covariance data into this data set, we could start to see that salinity curtain shift downward. Tidal exchange has also been now shown to be quite important. We generally see exports of dissolved carbon, both inorganic and organic. About half of the carbon that gets fixed on site gets lost. And it takes a lot of measurements to make this. This is not an easy task. But to do it, we're also finding that elevation is probably a good modeling component in terms of helping constrain the tidal prism, how much water comes in and out. Changes in elevation with relative sea level rise is currently our best predictor of carbon accumulation rates. Basically from 0 to 700 grams of carbon can be accumulated per year in soils. We're seeing that regionally it's really important, but within regions we still have a lot of variability. So it points to needs for better maps and models. And those models are coming from process-based and paleo-based approaches, which show that expected marsh gain and loss with changes in sea level rise and ecogeomorphic feedbacks can be constrained. These models are the kind that set expectations for stakeholders for what is and is not possible and or probable. I want to close by pointing out that all the outreach and synthesis works that have pushed coastal carbon science further and made it more useful have really focused on stakeholders. The National Estuarine Research Reserve funds blue carbon projects throughout the U.S. They were at the forefront of identifying this potential in reducing methane emissions and increasing carbon sequestration rates in soil by returning tidal restoration to previously impounded, thus freshened tidal wetlands. The U.S. Global Change Research Program integrated blue carbon into the continental landscape such that the whole aquatic continuum could be appreciated and pointed towards significant storage in the coastal ocean setting. The National Academy of Sciences included blue carbon as one technology among many and has called for greater research on resilience and manipulation, and pointing out that it is basically low cost compared to the other techniques for negative emissions. The regional carbon cycle assessment of the Global Carbon Project is basically started just recently, the second version, and it's generating and integrating published maps and databases of all coastal ecosystem types, and so it's improving representation globally. NASA in particular has pushed wetland observations and assessments for tidal marshes and mangroves, which point towards expected responses to global changes and also provide maps and data sets to improve assumptions and process-based models. I just want to finally point out the Coastal Carbon Research Coordination Network. It's in its third year. It's an all-inclusive community of practice to accelerate blue carbon research by sharing data and developing tools to understand and represent it. There's going to be a town hall on this. I highly recommend attending. Good news from them. And so finally, I want to point out that these advances keep coming. This decade is already moving forward on integrating these 4 M's: manipulative experiments, mapping, modeling, and measurement integration across scales. Of the 1,500 coastal talks in this whole AGU, 300 refer in at least part to blue carbon ecosystems. I hope that that will continue and that we have the bright future ahead of us. Thank you.